We will now run RAP in a civil aviation application, performing coverage calculations for air traffic control stations and for radars, and also performing some interference calculations of interest, in particular for civil aviation. So I will first place an air traffic control station at some location in the map. I'm not selecting it in any careful way. This is just to show the example of how a new station is created. RAP works with station templates, and the aeronautical ground default is good for this demonstration. It operates at a default frequency of 125 megahertz, which can be changed easily by the user. There are complete technical definitions of transmitter performance, receiver performance, and so on the tabs here. So this transmitter is 50 watt. It radiates 50 watts, and that is quite typical for this application. So the station is created there at that location. It also appears in the list of stations in the project workspace of RAP. Now we'll make a coverage calculation for it. I use the coverage tool of RAP. We will calculate field strength because that is a common way of doing it for air traffic control purposes. I define the aircraft which we are supposed to perform the coverage against, and let's use this one. It's at 20,000 feet above sea level, and this will require something around 300 kilometers of calculation range. We'll use a propagation model that is appropriate for this purpose. RAP has several propagation models to choose from, and what is important now is to have one that really can handle the high altitude of the aircraft. When I press OK, it starts calculating, and the progress is quite fast, and the result will appear in the results in project folder. We will make some settings first of the field strength to present, and typically for VHF communications, ICAO recommends designing for 45 dB microvolt per meter, so we will use that as the coverage criterion. This will be the field strength at the aircraft. I'll take away the other colors in order just to represent one field strength contour. So this is the calculated coverage for this air traffic control station communicating with an aircraft at 20,000 feet above sea level. Let's try this out for a real station also. We have a database of ICAO air traffic control ground stations here, and I will search that by using, I'll draw a map. In the map, I'll draw a circle. So let's search in that circle for contents of the ICAO database. So here we have a few, and I'll just pick one at Eldoret, which is quite near the station that we just created. So there it is. It operates at 121.5 megahertz. So let's see what the coverage is for that with the same type of calculation as the one before. I don't need to make any more settings now because we have done it once, and the tool remembers the settings. So I'll just calculate. And showing that in the map gives almost overlapping coverage because they are so close. So I can hide the first one and show this Eldoret station. So it is at the international airport there. Okay, I continue with an example of a radar station. So let's place a radar at this same location. I make use of the coordinates for the existing station with this command, and then creating a new station. Now we will do this as a primary surveillance radar, a PSR. So there it is, and give a name to it. This radar operates at around 2.8 gigahertz, and it has typical characteristics of a PSR. Okay, and then we perform the calculation by marking it and using the radar coverage tool. And let's put a target height. This will be the aircraft height of, let's say, 10,000 feet. That is 3,048 meters above sea level. Set the calculation area and set the resolution for the calculation, pressing OK. So now the calculation starts. This takes a little longer because I used very high resolution for the terrain, which is quite important for radar, because any terrain obstruction will totally obscure coverage for the radar. For secondary surveillance radars, we use the coverage tool because SSR is actually a transponder type of system, transmitting from the ground with aircraft responding to that. So it's that is more of a normal coverage calculation. It works the same way, very similarly as the first one, the coverage calculation for the air traffic control. So now the radar calculation is ready. It is stored in the radar coverage results folder. The display by default is for radar cross section, 1 square meter, 10 square meter, and 100 square meter radar cross section, and they represent different sizes of aircraft. So I stay with that and make it visible in the map. So this is the coverage. The red area is for a small aircraft with just 1 square meter of radar cross section, yellow 10 square meter, and green 100 square meter, which is represents a fairly large size passenger aircraft. And it is quite evident that the mountain here, where the cursor is right now, obscures coverage, and also a mountain ridge to the southeast also blocks coverage for the radar at this flight altitude of 10,000 feet above sea level. RAP also supports calculations for navigation systems such as VOR, ILS, and the DME SSR microwave landing system. It supports all those kinds of calculations. And NDB in the 300 to 400 kilohertz range is also supported. Now we'll make a demonstration of interference calculations. Interference is a difficult matter for civil aviation due to aeronautical safety requirements. One must make very sure that there is no intermodulation or interference problems in the installations. To do that, I open another project, an example where we have placed several radio stations within a very small area. The example here is placed at Arlanda Airport in Stockholm, Sweden. It does not really relate to real stations that are at Arlanda Airport, but the example will show how it works. So in this small area, all these stations are located. Let's check the interference for one of the aeronautical stations, and for instance the one operating at 126.65 megahertz, and see what kind of interference it gets from the other stations, and the reverse, what interference does it give to the others. We use the co-location interference tool for this. It now shows a list of all participating frequencies in the calculations. Pressing calculate and calculate interference gives a lot of interference indications, and the worst one is F. It has a total interference count of 16. So let's see what we can do with that one first. Lots of intermodulation. With these participating stations. Here we have a particularly difficult case in J, because the distance to the antenna is only 0 meters, so they are just on top of each other. So a first thing is to move the antenna a little. They can't be just on top of each other. So we'll move this antenna slightly. Let's put it at 14 meters. We will do some more things, intermodulation. The good way to handle that is to put filters on the equipment, narrow band filters, so we will do that. I now place narrow band filters on the participating transmitters. So let's have a look at this filter. It is quite selective, quite narrow band, and should provide some reduction in intermodulation. Let's have a look again which other contributing stations we had. Okay, J, H, E, and it's very probable that they also will need filters. So let's put filters on them, the same type. H, and E. Having changed data, we get an information message, station data changed, recalculate. So let's recalculate, and let's remember that it was receiver F that we looked at. See how it well, now receiver F has disappeared here, so this means that the receiver F is clear of interference. We fixed that, and this may then continue with others. Receiver K. Okay, let's put filter on it. It is right on top of transmitter I, 0 meter separation. So let's fix the antenna. Let's just move it a little. Usually not much difference in antenna height is required in order to fix a situation like this. In addition, put a filter on it. F already has filter, so we don't need to do that. Okay, recalculate, and let's see if K works fine now also. Yeah, it does. So continuing like this, it is possible to get a clear non-interfered situation. Now G is the worst one, so let's fix it. F already has filter, and most probably the others have also. So I'll just check. Yeah, they have. Recalculate. And so on. It's easy to continue and see what difficulties the others have. And this co-location interference tool considers many types of interference, harmonics, intermodulation, both receiver and transmitter. It considers blocking, that is receiver severe overload, and it considers adjacent channels interference from transmitter noise and receiver selectivity. There are other tools that are useful for the aeronautical applications in RAP. The frequency assignment tool, for instance, but often frequency assignments are determined at an international level, at ICAO, leaving little freedom for the national civil aviation authorities to change frequencies to minimize interference. Other means may then be necessary for reducing interference, such as what we just showed with proper RF site engineering. RAP supports multiple databases. The example here was the ICAO VHF communication database. There are others like the ILS VOR that can also be connected. HF communication frequencies are maintained by the ITU, and this database, the International Frequency Information Circular, contains information on such stations. In the way of microwave links that may be used for aeronautical purposes to connect, for instance, a communication site to a communication central. RAP also supports that by the radio link performance tool. So all in all, it is a very complete software to handle civil aviation applications.